a single market order to buy 1,000 shares of XYZ was filled twice, resulting in 2,000 shares bought and a negative account balance. The root cause? A race condition in the matching engine's ReadWriteLock. Here's exactly why. Let's start with the basics of how an order book works. Welcome to TheCodeForge. Before we dig into that production issue, let's design a stock exchange. A stock exchange is a system that matches buy and sell orders for financial instruments. The core is an order matching engine that maintains an order book, enforces price-time priority, and executes trades with strict consistency and low latency. The order book holds all resting orders. Bids are sorted by price descending then time, asks by price ascending then time. Each price level has a FIFO queue. We use a ConcurrentSkipListMap for sorted iteration and concurrency. Here's the basic order book with a course lock. Notice we use long for price to avoid floating point errors. The ConcurrentSkipListMap gives us sorted iteration. This is a starting point, but the single lock will be a bottleneck. When a new order arrives, we check if it can trade against the best opposite price. If yes, a trade occurs at the resting price. We reduce quantities and remove filled orders. This loop continues until no more matches. Here's the matching loop with a course lock. It iterates over price levels, matches orders, and adds any remaining quantity back to the book. This works, but the lock serializes all orders. To achieve sub-millisecond latency, we need lock-free data structures. We use a ConcurrentSkipListMap for price levels and concurrent linked deck for queues. Each order has an atomic reference status, so we can atomically transition from active to matched using CAS. In the lock-free version, we use CAS on the order's status. Before matching, we atomically set status to matched. If the CAS fails, the order was canceled or already matched, so we skip it. This avoids locks entirely. Every trade and order book change must be published. We use a disruptor pattern ring buffer to avoid locks. The matching engine writes events to the ring buffer, and a separate publisher thread sends them over UDP multicast. Never block the matching engine on network I/O. Here's a market data publisher using the LMAX disruptor. The matching engine publishes events to the ring buffer, and the event handler sends them via UDP. This decouples the matching engine from network I/O. An order goes through several stages: validation, risk checks, matching, trade reporting, and settlement. Each stage is a separate service communicating via Kafka topics. The matching engine is stateless, reading from a queue and writing trades to another queue. Before an order reaches the matching engine, it must pass risk checks: max order size, position limits, price collars, and circuit breakers. These checks are critical and must be fast. Never do risk checks in the matching engine itself. Here's a simple risk service that checks price collars and position limits. It uses in-memory state for speed with a write-ahead log for recovery. The matching engine must be durable. Every order and trade is logged to a write-ahead log before processing. On restart, we replay the log to rebuild the in-memory order book. Batch flushes improve throughput at the cost of losing up to 1 ms of data on crash. Here's a simple write-ahead log using a file channel. We write each order to the log and flush periodically. The log is the source of truth for recovery. This is the same issue we highlighted at the start. Here's exactly why that happened. The matching engine used a ReadWriteLock. During a concurrent cancel and match, the cancel thread removed the order and released the lock, but the match thread had already read the order as valid. The match proceeded with a stale reference, filling an already canceled order. The fix was to switch to a lock-free order book using atomic compare and swap on order status. Before matching, the engine atomically sets status to matched. If it's already canceled, the CAS fails and the match is aborted. This prevents double fills. This is the exact mistake from the incident. The lock was released after reading, allowing another thread to modify the order. Always use atomic state transitions on the order itself. The ABA problem can occur if a node is removed and reinserted with the same address. Use atomic reference with versioning or a hazard pointer to avoid it. Never use floating point for prices. Rounding errors can cost real money. Always use long with a fixed decimal multiplier, like cents. Never block the matching engine on network I/O. Use a separate thread or disruptor to handle publishing. If the network is slow, drop packets with sequence numbers rather than block. Risk checks should be a separate service. Putting them in the matching engine adds latency and couples concerns. Keep the matching engine focused on matching. The article mentions per price level locks as a compromise, but doesn't show the code. Here's a concrete implementation using ReadWriteLock per price level, which allows concurrent reads and exclusive writes per level, reducing contention compared to a single global lock. The article uses ConcurrentSkipListMap with collections reverse order for bids. Note that ConcurrentSkipListMap does not support null keys or values, and its iterators are weakly consistent. In Java 8+, the reverse comparator works correctly, but ensure you are not using a custom comparator that violates the comparable contract, as it can cause undefined behavior. The article assumes a single order book, but real exchanges shard by symbol to scale horizontally. Each symbol has its own matching engine instance, often pinned to a single CPU core. This avoids cross-symbol contention and allows independent scaling. The article's lock-free or per price level designs apply per symbol. The article mentions idempotency, but doesn't show code. Here's a pattern using a unique order ID and a deduplication cache, e.g., a concurrent hash map with TTL to prevent duplicate processing from network retries. When things go wrong, start with the logs. Check if an order was canceled or filled. For duplicate trades, query the database. For stale market data, check the publisher's ring buffer. Let's run through some common interview questions. How does the engine handle concurrent cancellations and matches? Use atomic CAS on order status. When to choose lock-free vs per price level locks? Lock-free for ultra-low latency, per price level locks for most systems. What happens when a market order has insufficient liquidity? Match until book exhausted. Use price collars to limit slippage. And a few frequently asked questions. How does the matching engine work? Price time priority, highest bid, lowest ask matched first. Difference between limit and market orders. Limit order guarantees price, market order guarantees execution. How to achieve low latency? Lock-free structures, kernel bypass, single-threaded per symbol, disruptor for publishing. To recap, price time priority is the only fair algorithm. Use lock-free structures for low latency, but per price level locks are fine for most systems. Always use atomic state transitions on orders to prevent race conditions. And never forget the WAL for durability. Ready to go deeper? Up next, design a code deployment system, then design a distributed cache, then design a distributed locking service. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.